it's time we pulled everything you learned together. So we're going to look at the planetary circulation this week. And planetary circulation is really just looking at the globe as a whole and averaging everything out over time without any small perturbations or things flowing through it, which there are lots of. So the idea is to see what is, if you were to look at the globe at a snapshot over the course of 100 years, what would the circulations look like? Well, they're going to kind of follow a pattern, and we're going to use the sun is really kind of the key to this. We know that the sun heats up more at the equator and less at the poles. If the Earth didn't rotate, obviously, one side of the Earth would always be dark, lose lots of radiation. The other side would always be light, have plenty of sun, and it would be hottest at the equator. So, and we'd have what we call one big circulation, running from where the hottest is to the north, lifting the air, rising there all the way around to where the darkest and coldest is, sinking there and coming back around. However, the Earth rotates. So that means it splits it up. Remember, the winds are reflected to the right in the northern hemisphere and to the left in the southern hemisphere. And what do you get? Well, think about it. You get trade winds. We call them trade winds down here between 0 and 30 degrees north. More of westerlies, 30 degrees to 60 degrees north. And more easterlies north of 60 degrees north. Notice a couple things here. The winds are converging towards the equator. That's where the intertropical convergence zone is. However, they're diverging, pulling apart around 30 degrees north. So the winds tend to sink right there. We get lots of high pressure right around 30 degrees north. Get lots of low pressure around 60 degrees north. So, and now think about this. The sun moves 23.5 degrees to the south and 23.5 degrees to the north throughout the course of a year. The equator, as far as the sun is concerned, is actually moving that amount. So you're basically going to be shifting, at least somewhat, where these planetary circulations are, depending on summer or winter. So, as you can see, we have the high pressure. Low pressure is around 60, and low pressure around the equator. And you look at a weather map, and you see a big high pressure generally over the Atlantic Ocean here, especially in the summertime, in the wintertime in January, when it might even be pulled fairly far south. In the summertime, it kind of makes a little bit further north, and it's kind of called the Bermuda High in the summertime. And we have low pressures up over Greenland in the winter, in the summertime, and they tend to come a little bit further south in the wintertime. The southern hemisphere doesn't have as much land, so it's kind of more uniform. Remember, the oceans don't change temperatures as much, so you don't get flux as far north and far south. So there's big subtropical anticyclones. It used to be when the sailing ships were the way people moved across the oceans, they didn't want to get into the doldrums, and the doldrums were right around 30 degrees north and 30 degrees south. They would much rather be south or north of those. When they got into that area, there would be almost no winds. A couple things, too, about these. Because they're huge over the ocean, the eastern sides of them have a lot of compressional warming. They sink. There's very low relative humidity there, fair skies. And this is where the deserts are. Think about it. One of the biggest deserts in the world, Sahara. On the eastern side of the Atlantic Ocean, on the eastern side, it's around 30 degrees north. Another desert, southern hemisphere, is actually down in Chile. Very, very dry. So there is not a lot of rain on the eastern side. There are the polar lows. We've been talking a lot this winter about the circulation around the northern North Pole and how it broke up and completely went away for a while and then came back now, and how that influences our weather. That polar vortex, how it changes, has a major impact on how cold we may get or how warm we may get. Then we're in the mid latitudes. Winds generally move from west to east, and they're in a ridge trough pattern, just like waves. Not nice and uniform wave necessarily, but they kind of move that way. They have a wavy pattern to them. And depending on which part of that wave you're in as to what weather you're going to have. So let's take a look at the tropopause. We know tropopause is always highest over towards the equator. And between 0 and 30 degrees north, there really isn't a tremendous amount of temperature change, especially in the summertime. So with that in mind, the tropopause is uniformly high there. However, to the north, let's go north of 60 degrees, the polar vortex is in place. It's extremely cold there. So what happens? The tropopause lowers. Now we come to our latitude. Our latitude has fronts passing all the time, moving up and down across the area, warm front, cold front. When they're doing that, they're constantly changing the shape of that tropopause so that it fluctuates up and down depending on whether a front is coming through, a low pressure system is moving. So while yes, it's lower than the tropics, it's not as low, and it's definitely not as uniform as either one. It changes a lot. Trade wind inversion. South of these big lows, big highs, think about them, they're rotating clockwise. So you have a nice steady east wind. As they move across the ocean, they pick up moisture, but they're very, very stable on the top part of the layer, usually. When there's very low SSTs around, especially, they can just be cool, humid, very stable. And that happens a lot in the western parts and the eastern parts of the ocean, excuse me. Think about Los Angeles, California, San Diego. If you try to go swimming over there in the ocean, it is cool. However, try going swimming in Charleston, South Carolina. Yeah, warm water is fairly comfortable, very warm. That's the difference caused by these circulations. The SSTs get very warm, the air becomes more unstable, especially on the western side of these lows, and the trade winds begin to mix. That's why we get the tropical systems on that part of the ocean, more to the western side of the Atlantic than the eastern side of the Atlantic. Oh yeah, you think about it, that's why over in the Pacific there are hardly any hurricanes there by the western United States. However, if you go towards Japan, there's a lot. Other thing with this is that the intertropical convergence zone moves a lot. And its motion is basically like the weather equator, we'll call it. And when it moves north, it changes how the wind flows. Almost like you move into the southern hemisphere flow for a little bit and then back into the northern hemisphere flow. And with that, notice it changes not much at all over the oceans. Why is that? Because the oceans take a lot to heat up. They don't actually have a lot of temperature change. However, over land, and especially over Pacific, over Indian Ocean, there is a tremendous change. So with that, it causes a monsoon there. When it moves north in the summertime, India is on the south side of the intertropical convergence zone. Winds are converging into that intertropical convergence zone from the south. So you get a lot of flow off the water, lots of moisture. Wintertime, that intertropical convergence zone has moved south of that area. What happens is you don't get as much rain, get drier. So you can see these monsoon are long-term circulations. And they impact the ocean. These highs are there all the time, and they actually have caused circulations in the ocean. We have a Gulf Stream that runs up the east coast of the United States with lots of warm water. Think about it. There's circulation, the high pressure here. It has caused that Gulf Stream, and it actually triggers some of that warm water to head towards England. It actually helps keep England a little bit warmer than it might otherwise be. However, in the Pacific, water is coming down from the north along the California coast and getting colder. So you wind up bringing cold water from the north there. There's another monsoon that actually occurs in the U.S., also North American monsoon. What happens is the mountains in Mexico, and there are high mountains out here in this western part of Mexico, get very hot early in the summertime. When they get hot, the air rises, causes low pressure system right there to be stationary almost, and pulls in moisture from the Gulf of Mexico, which then translates north. Oh yeah, when it gets hot at the bottom, remember, very hot air means pressure is going to fall slower aloft. So you actually wind up with high pressure aloft, which just traps this moisture down near the ground and keeps it there and keeps pumping it into Arizona, New Mexico during the summertime. That's when they get their heavy rainfalls. Okay, Rossby waves are really looking at an upper atmosphere wavy pattern. We're going to look at those in a minute here. But there are waves always going across our area in the upper atmosphere. There's a zonal flow when the waves are very not that deep. However, you can still get low pressure systems with them along the waves. And when they're meridional, and guess what? We had a meridional flow last month in February when it got so ridiculously cold in Texas, all the way down in that area. That was a meridional flow because it pulled the cold air out of northern Canada all the way down to Texas. Sometimes these patterns get blocked. And kind of what happened when it stayed cold there in the Midwest for a long period of time was a blocking pattern. It did not want to move to the east or the west. When these blocks set up, sometimes they can last for weeks. In 1993, there was a big blocking pattern in the Midwest. High pressure was to the east, low pressure was to the northwest, and what you did was feed in moist air off the Gulf of Mexico along a front that didn't move. Well, guess what? Last week we had kind of a blocking pattern. We had lots and lots of rainfall from Texas, basically starting in Arkansas all the way into West Virginia. Tremendous flooding event during that. The pattern didn't move. That front didn't go anywhere. So that's a blocking pattern, and it can cause significant precipitation along it. Jet streams. All right. When you have warm air at the surface, the pressure is going to decrease slowly with height, right? So you basically can have a higher pressure up there, but sometimes high pressure and atmosphere aloft can be over a cold area as well. But if it's extremely cold, you tend to have lower pressure, especially the atmosphere tilts. So that lower pressure is actually to the northwest of a high, a very cold high. So you wind up with a very strong pressure gradient up at loft. And that pressure gradient in the loft is where the jet stream forms. The greater the contrast in temperature, the greater the jet streams you're going to have wind. So that means it's going to be further north typically, especially in the wintertime. It's going to be across the United States. In the summertime, that's going to be pushing it back up to the north, probably across Canada. And remember, the Coriolis effect impacts this jet stream. So if you have a lot of snow cover, it can move the jet stream south because you have very cold temperatures pushing it there. And you can see the seasonal shifts here. One other thing about a jet stream is there's convergence and divergence along it. And they ripple along these Rossby waves, the jet stream does. Divergence is to the left front of the jet stream, and divergence is to the right rear of the jet streak. A jet streak is where just the highest winds are along a jet stream. These winds can reach up to almost 200 mile an hour at around 250 millibars. Tend to be a little lower in wintertime, like 300 millibars, and be a little higher in summer, closer to 250, 200 millibars. Where that divergence is, what's happening at the surface? Well, winds have got to lift from the surface up to take the place of where that divergence is. So that is where your low pressure systems, your extratropical lows, are forming along these type of circulations. There's another aspect to the global circulation: El Nino and La Nina. And these are the historical trends of it. It goes up and down. And you can see we get periods where we have several years of El Nino and several years of La Nina. We've been in actually an El Nino. A La Nina this last winter and last summer. And one of the things La Nina does, it's kind of caused by the spirals that go on in the water. The oceans also have Coriolis effect impacting them, and they create an Ekman spiral. What happens is you have the wind coming out of, say you're in Charleston, South Carolina. Actually, let's go to the Outer Banks of North Carolina. Corolla, for example. If the wind is southwest in Corolla and been that way for days, the water is going to tend to move to the right. So instead of being the nice normal southerly flow you got along the coast, it's going to become more east out over the water. It's going to move more west from the west, and eventually it's actually going to loop all the way around. The further down it gets, till it actually comes back towards the shore. So what that does is lift the very cold water from the bottom up, creates upwelling. This happens along the equator. It happens along the coast sometimes. And in Corolla, I have friends that go down there surfing a lot. And there'll be days when it's 80-degree water temperature, and a couple hours later it'll be in the 50s, due just to this impact of the Ekman spiral. Warm phases of El Nino. It changes. El Nino was named because it really messes with the fishing that it goes on off of Chile, off of parts of the U.S., and it changes up that fishing so much. Because of that, what it really impacts is the water temperatures, and that causes, if it's very hot, there's a lot more thunderstorms over the ocean. A lot more moisture is available to move east into the eastern U.S., and it actually triggers very strong winds in the lower latitudes. The trade winds actually enhance. When that does, it actually inhibits hurricanes in the summertime. Now, La Nina, on the other hand, decreases those winds. It tends to have more storms coming in the northern Pacific. And this year we had an El Nino year. And what happened? We had a lot of storms going into Seattle, into Portland, Maine. They didn't come into California as much. It was a relatively dry year in California. So, and La Nina isn't quite as intense usually. It's usually a couple degrees below normal. But it changes everything as far as how the circulations go across the United States. It has an impact, particularly in the wintertime. The summertime impact is more on the tropics. Another one, long-term anomaly that we look at, is North Atlantic Oscillation. The North Atlantic Oscillation is looking at high pressure and low pressure over Iceland. And depending on how they go, we can get a lot more winter storms on the East Coast, a lot of nor'easters, you would say, and a lot of cold air in the eastern part of the United States. They have a major influence on the winter weather in the eastern U.S. And depending on whether they're positive or negative index, is just how they're going to deal. The colder they are, the more the low is intense up there, maybe bringing in a lot more cold air, more snowfall. And we actually track them, and it's very difficult to forecast how that's going to take shape throughout the winter, and it has a huge impact on our winter. The Arctic oscillation, again, that polar vortex circulation, how it fluctuates is another issue. So with that, let's move on to, there's Madden-Julian oscillation as well. That is basically just a major cluster of thunderstorms that develops typically over the Indian Ocean, the Eastern Pacific Ocean, and then really translates around the globe. You can actually, we know now, as we're learning more about these MJOs, that actually can trigger extratropical cyclones over the United States, over Europe, and they really can be some of the more intense ones. We're trying to understand how that all works, and there's still a lot of research being done. Here, for example, was our Arctic oscillation. When it's more positive, it's a more intense circulation. More negative is less intense. Well, guess what? When we had our really cold air, we had a very, very negative one. So that is what allowed all the cold air to come in. But sometimes it's neat to look back at these and see, and to try to forecast how they're going to change. Now that we're getting closer into spring, the changes will become more subtle, and they won't have as big an impact as they do in the wintertime. So if you were to look at La Nina and El Nino, here are the sea surface temperature anomalies right now. In order to declare something an El Nino or a La Nina, you have to have 3 months of either above normal and at least a half a degree above and or half a degree below normal. Notice how we've been running below normal since August. And El Nino 3.4 is the region they look at. We've been running around up to about a degree and a half to a degree below normal so far. And it doesn't show signs of really changing a lot yet. The idea is all the models are forecasting it to transition to neutral during the summer, but we'll have to wait and see on that. Looking at global circulations can be kind of interesting, and this is kind of a messy chart, sorry. But there's low pressure, basically around 50 degrees north here. And there's big high pressure right over the poles, under the polar vortex. So, but extremely, extremely cold so that the pressure really has dropped. Notice down here around 30 degrees north, high pressure, high pressure. So you can actually look around the globe and you can see these planetary circulations there. And really, they show up more in the high pressure than the low. But look at all the lows. There's one right here, another one over here. All these lows around the north, very close to 50 to 60 degrees north. High pressure is around 30 degrees north. Here is the jet stream and looking at what is a very complex Rossby wave pattern. We have one low, Rossby wave over the western part of the Pacific, I would argue right here. We have another one over the eastern part of the U.S., kind of keeping us on the cold side right now. We have another one over Europe, western side of Europe. And you see in that are these jet streaks. Here's one. The darker the blue towards purple, stronger winds. Here's another one. Here's another one on the East Coast. And sometimes the jet streak way down south here, it's called the subtropical jet streak, moves across to the southern part of the United States many times and can influence bringing precip into the Gulf of Mexico. And if they merge and get caught into these big systems here, they can bring a lot of nor'easters or strong lows into the Midwest. In this case, they're very separate, and we actually have low pressures that have been driving across the Gulf of Mexico and across Florida, bringing a lot of rain there, but not much coming up north. Finally, just looking at 250 millibars right now, the jet streams, and you can see there's a southern one and a northern one. And here is your jet streak. If you were looking for lows, you would look here, left front, right rear. So right in this area somewhere you would expect to see a low pressure, kind of towards the little bit on the east side of the main trough of low pressure. Here's another area out here in the Pacific as well. And here is one down in Texas and moving across there. So if we were just to look to see if any of this was working out, we could take a quick peek here at WPC weather and see if there's anything at the surface showing up. And if it ever comes up here, we can take a fast peek at that. And then I think I've got it. That's about it. We do see, as it's filling in the gaps here, a little bit of a low pressure. We were looking at that off the coast due to that. And this thing is just not going to be moving very fast today. And notice down here in Texas, where we were in that area, we were talking about lows moving across there as well. So it actually does work. So if you have any questions about all this, and I know this is a lot of material this week, please don't hesitate to ask.